I'm here to present a seminar with titled Some Real-World Applications of Numerical Optimization under this important platform of the church cluster from Nigeria. Thank you very much for inviting me to present in this wonderful research group. So these are the outlines of my presentations. Now let me start with introduction. Numerical optimization is the process of finding the best solution to a problem subject to constraints. And it plays a crucial role in engineering, where in engineering it is used for structural design, control system tuning, and electronic circuit optimization. In finance and economics, portfolio selection, risk management, and supply chain logistics rely heavily on optimization techniques. Healthcare applications include treatment planning, irradiation therapy, drug discovery, and medical image reconstruction. Optimization also underpins energy management, such as optimal power flow in smart grids and placement of renewable energy systems. In addition, everyday technologies, including navigation systems, scheduling, and parameterized documentation, and it is fundamentally driven by optimization algorithms. Also, robotic path planning and trajectory optimization to minimize energy consumption or to minimize accuracy, and sometimes to minimize the error that robot can occur during when performing the tasks. These type of applications highlight the importance of developing efficient and robust optimization methods. A typical nonlinear system equation can be expressed in the following form. So in this area, we are solving the problem of equation 1. So we are looking for the value of x such that f of x equal to 0, where f is a nonlinear mapping from Rn to Rn, which is assumed to satisfy the following assumptions 1, 2, and 3. Now, definition. Let S and Y in Rn be a mapping. Let S and Y in Rn, then a mapping F is said to be monotone if the function F satisfies equation 3. However, problem 1 is called monotone system nonlinear equation if F satisfies equation 3. So we have general function and we have monotone. So in this presentation, we are more focused on solving the nonlinear monotone equations. The study of monotone mappings are practically applied in many scientific fields, such as chemical equilibrium equations. In chemical equilibrium equations, it's very challenging because of the complex nature of chemical systems. These equations show how reactant and product balance each other in chemical reactions, including their concentrations and the condition for reaching equilibrium. The complexity comes from the nonlinear characteristics of these equations, which can lead to several possible solutions and will be very sensitive to initial conditions. To address these challenges, researchers use monotone nonlinear equations as a helpful tool. By applying properties of these equations, they can systematically tackle equilibrium problem, ensuring that solutions constantly converge. This method offers a clearer understanding of chemical system behavior and enhances the accuracy of prediction and analysis regarding equilibrium states. Another application of monotone linear equation is signal recovery. Nonlinear optimization is a vital process in signal recovery, and it plays a key role in reconstructing and enhancing signals that have experienced degradation or distortion due to various factors such as noise, interference, or signal loss. By leveraging sophisticated mathematical techniques, nonlinear optimization method adaptively minimize errors and significantly enhance the quality of the recovered signal, making them clear and more accurate. These methods utilize nonlinear optimization algorithm to identify and remove unwanted noise from the original signal. This, this capability is essentially valuable in communication and audio engineering, where precise and reliable signal recovery is essential for maintaining high performance standards. In these domains, the ability to restore signal to their original clarity can impact the overall effectiveness of systems, leading to improved user experiences and increased operational efficiency. And another application of nonlinear optimization is image restoration. Numerical optimization techniques are vital for restoring images and improving their quality when they are affected by noise, motion blur, or compression artifacts. These techniques use mathematical algorithms to reduce differences between damaged and original images. Optimization method like gradient descent algorithm enhance image quality by refining details and reducing flaws, resulting in sharper images. This clarity is vital in medical imaging for accurate diagnosis and satellite photography for effective environmental monitoring. Additionally, these techniques are crucial in digital forensics for recovering visual evidence from altered images, alternatively improving effectiveness of various applications. Now, the commonly used iterative scheme for solving problem one is in the form of equation four. So since we are doing with, we are solving the solution, and we know sometimes that solution is not easy to obtain. So we are going iteratively to solve the problem one, where sk plus 1 is the current iterate, sk previous iterate, alpha k the step length, and dk the side direction. Newton method is a well-known method for finding the solution of equation 1. And Newton has the following direction equation 5, where f prime of sk is the Jacobian matrix of f of sk at sk, and Newton method generating the sequence of iterant via equation 4. The attractive features of Newton method are rapid convergence and easy to implement. However, Newton method has the following shortcomings. The shortcoming number one is the cost of computing and storing of the Jacobian matrix at each iteration. Because if you look at equation 5, we have the Jacobian matrix, and we know Jacobian matrix is a matrix of derivatives. So sometimes some derivative has no analytic solution. That's one of the drawbacks of Newton method. However, if you look at equation 5, we are taking the inverse of the matrix. So when the determinant of 0, then the matrix is singular. At that point, also Newton method cannot be applied because the matrix, the Jacobian matrix cannot be invertible when it is singular. So to overcome the difficulties of Newton method, it is modification have been introduced, like Peace Newton method, which it is side direction is given by equation 6. So the, the only different, the reason behind this Peace Newton method equation 6, when we computed Jacobian matrix at first iteration, that is when k is equal to 0, in the subsequent iteration, then we'll be using the initial data Jacobian matrix f of s naught throughout the iteration. Although this method avoids computation and storing of Jacobian in each iteration except at k equal to 0. However, it requires solving a system of nonlinear equation which consume more CPU time at the time of system dimension increases. Yes, because since it has a matrix, solving the last scale problem is another issue. Because when we have, for example, 1000 by 1000 dimension, we may have like 1 million entries or 10 million entries. We know that this machine cannot store that storage of Jacobian matrix. So In such, also, Peace-Newton method cannot be applied when solving the large scale problem. A quasi-Newton method is another variant of Newton time method that replaces Jacobian or its inverse with an approximation which can be updated at each iteration, and its stack direction is given by equation 7, where BK is the approximation of Jacobian at SK. So the Jacobian family, in quasi-Newton family, instead of computing the Jacobian matrix, they have approximated the Jacobian with a matrix beta k. So matrix beta k is just a matrix which has no derivative. The rationale behind a quasi-Newton method is to do away with the evaluation cost of the Jacobian matrix, because in quasi-Newton method we don't have derivatives, but still we have matrix. Even though quasi-Newton methods are derivative free, but still requires a computation of matrix at each iteration. Therefore, they are not ideal for solving large-scale problems. Furthermore, the matrix can be singular at a certain point during the iteration process, because if you look at equation 7, also we are taking the inverse of the matrix BK. That's another problem. If the matrix is singular, it cannot be invertible. So as a result, researchers are trying to produce a beta k which is symmetric and positive definite matrix. Because if the matrix BK is symmetric and positive definite, it is invertible. But it's not a simple task to produce that quasi-Newton object that can be symmetric and positive definite at each iteration. There are many formulae for updating beta k, but the most popular ones are BFGS, named for its discoverers, Broydin, Fletcher, Godford, and Chanot, and the symmetric Racon, respectively defined as first bullet and second bullet. The two update generate symmetric matrix. Moreover, if the initial approximation B naught is positive definite and the SK transpose YK is greater than 0, that is the denominator of, we call it a curvature. If the curvature is greater than 0, then the BFGS update generates a positive definite Jacobian approximation. So BFGS is one of the successful quasi-Newton update because it is generating symmetric, it is symmetric in nature, and also it is generating positive definite matrix at each iteration. But for the SR1, that is not the case. It can be positive definite in some clearly if you look at SR1, it is symmetric, but it is not necessary, it is not guaranteed for that definiteness at each iteration. So in some iteration it can be for that definite, and in some iteration it may fail. Due to the well-known shortcomings of Newton and quasi-Newton method, conjugate gradient method are developed, where the sequence of point is generated by equation 4 and the stack direction dk is given by equation 8. So the conjugate gradient method is one of the successful methods for solving the large scale problem, because in conjugate gradient method there is no computation of any matrix, so it is matrix free. And the rationale of any conjugate gradient method is produce a conjugate gradient parameter beta k. So different object of beta k reduced to different method. Some of the most famous conjugate parameters are listed as follows. We have Fletcher Ribs, which is introduced in 1964. We have Heston and Steeple, it's called beta KHS. We have Folek Ribery, which is called beta KPRP, among the many more. Now we want to develop an algorithm using conjugate gradient method, and also to apply that method in one of the application of optimization, that is an image delivering or recovery problem. So this is the method. Image delivering problems through accelerated Hagazan projection method for convex constraint monotone nonlinear equation. This Haggen projection method is one of the successful conjugate gradient method. Now, let F from Rn to Rn be continuous and monotone mapping, and omega be a subset of uh, subset of Rn. We hope to find a point S star in omega so that equation 9 has satisfied. The feasible set omega is assumed to be non-empty, closed, and convex set. Problem 9 is known as nonlinear monotone equation with convex constraints. Now, let us consider the method proposed by Waziri et al. Waziri et al. Proposed the Haggen CG parameter. CG means conjugate gradient parameter, defined as equation 10. So in their works, they have proposed this CG parameter in equation 10. But now we look at the limitation of this equation 10. Because for the general function, the CG parameter equation 10 may be undefined as some iteration when the denominator becomes 0. That is one of the disadvantages of equation 10. When for general function, the denominator can be 0. And if the denominator can be 0, then there's an issue. You cannot apply it to solve the general function. So for this reason, we are motivated to propose the following modified Haggen CG parameter. So we have proposed the CG parameter name that is namely beta k a head zp in equation 11. And in this equation 11, we have shown that our denominator here, sk minus 1 transpose k minus 1, is strictly greater than 0. So, and we have equation from there. We defined equation 12 and equation 13. And equation 13 is even the main work because for every Haggen method is the main reason behind the beta k Haggen CG parameter, Haggen CG parameter is to find the value of this theta k. What it is optimal value is yet to be found. So it's an open problem. A lot of researchers are working to find the value of this theta k that can give an optimal value. And this theta k, it is very important in showing the distance property, which is a crucial property achieving the global convergence. So we want to develop a method that is globally convergent. So as a result, we have this equation 13 and 14. For equation 13 and 14, we have shown that clearly the denominator of our beta k equation 11 is strictly greater than 0. So we have filled that gap of being a singular division by 0. Sorry. Now, before we get into the details of algorithm, let us define the operator. And actually, the derivation of find this equation 13 has been omitted in this research because it is a long derivation. So time will not allow me to follow the derivation step by step and explain. So we have just picked the result because it's a long derivation when obtaining this equation 13. Now, definition, let omega be a subset of Rn. Then for any S in Rn, it is projection onto omega as given by equation 16. We call this omega P of omega projection operator. Then the mapping P omega is known as the projection operator, which has non-expensive property. That is, for any Sy in Rn, it holds that equation 17 holds. Consequently, we have equation 18. Now, this is a proposed algorithm. These algorithms that we have proposed in this work. We name it algorithm 1 or A-head ZP algorithm. Now, before you go to the numerical, also there is convergence analysis, which is also omitted in the presentation due to the time constraint, because we have shown that our algorithm is globally convergent. Now, let us consider this assumption one. Assumption one, we assume that our function is uniformly convex or uniformly monotone as equation 21, and also the mapping F is elliptic continuous as in equation 22. Now, let us apply the proposed algorithm in application. Sorry, this is not a signal and image restoration. So this is not signal, it's image restoration. So a convex unconstant optimization problem, equation 23, represents the most prominent optimization problem in signal or image recovery. And as shown by Zawel et al., problem 23 is equivalent to the following nonlinear equation defined by 24. So Zawel et al., they did a very nice work because we know here we have num1 and we know num1 is not differentiable. That's why we have this tau, which is a linear operator. So as a result, they have transformed this equation 23 to equation 24. Also, it's a long work. There's a lot of transformation between 23 and 24, which is also omitted in this presentation because it is already in the work of Zawi et al. Then the function f, then Feng et al. Showed that the mapping f, this mapping f is elliptic continuous and monotone. And remember, in our assumption one, we assume that our function also to solve our problem is elliptic continuous and monotone. So since 24 is elliptic continuous and monotone, and 24 is transformed from 23, so problem 23 can be translated into problem 9. That is problem 9, our problem f of s equal to 0, because they have the same property. Therefore, our algorithm ASZP can be applied to solve problem 23 because they have the same property. To further highlight the performance of the proposed algorithm ASZP, so numerical experiments were carried out. And numerical tests were performed to demonstrate the effectiveness of our algorithm by restoring certain blurred images comparing with SGCS method. So we have compared our algorithm with the existing SGCS method in the literature. When implementing our algorithm, we use these parameters, and also the parameters of SGCS algorithm are taken as in their favor, in their work. So the iteration is set to stop for both methods if the following condition 25 occur. Also, signal-to-noise ratio is defined as equation 26, where S curve and the S are the original image and the restored image respectively. In addition, structural similarity index, known as SSIM, is used in this paper in order to measure the quality of the restored image. And the multiple implementation of the SSIM index can be obtained at this website. And this SSIF of the original image is 1. So the method that has SSIM, which is very close to 1, so is the best, it is method that recovered the disturbed image than the other one. And we have this, we have implemented this numerical result, this experiment with 4 figures, figure 1, 2, 3, 4, and the different sizes of the same size of photo. And if you look at this table, we can easily see that our method recovered the disturbed image with less number of iteration and CPU time than the compared SGCS method. And if you look also at the SSIM, the similarity index, our own is higher because it approaches 1 more than the compared method. This shows that our method, apart from removing the disturbed images also, it performed better than the existing method in the literature. Now, if you look at this figure, we have original image, we have the blurred one, which is disturbed by noise. And this the algorithm is our algorithm is that remove the noise, we remove the noise, and also this the SGSC method, also SEM method, has also successfully removed the noise. The same tool, this figure 2, we have original blood and AZP and the SDSC recovered by our method and recovered by compiled method. The same thing with this heart image. Also, we have this for lungs. We have original blood recovered by our algorithm and recovered by SGSC method. Then conclusion. Key features of the proposed method: it is fully derivative-free iterative method, so it is capable of handling large-scale problems. So it has no computation of the Jacobian matrix at each iteration, resulting in its low memory requirement and reduced computational costs. Also, the AHZP method has been successfully applied to image deblurring problem, achieving superior restoration compared to the SGCS method reported in the literature. And we know optimization is equal to better decision, better system, and better future. Future work. In the future, we want to extend the proposed method to all the large-scale applications such as variational inequalities, optimization problem, and differential equations. Also, we want to develop adaptive strategies for selecting the conjugate gradient parameter beta k to further improve convergence speed. Also, to explore additional real-world applications, including signal processing, machine learning, and the motion control model. Thank you for your kind attention.
Thank you very much, Dr. Abubakar, for this very interesting and eye-opening research. And I must, appreciate your application and for, presenting to allow us see the applied side of mathematics, applying it in medical imaging and reconstruction, and also in picture recognition. Okay, so before we take some comments and questions, I would just like the director of the National Mathematical Center to give some comments. And if he has a question, Dr. Abubakar will be glad to respond to them. Prof, sir, are you available?
Yes, I'm available. Good morning.
Yeah, good morning, sir.
Right, I think it's a very good presentation, particularly now that you're utilizing mathematics to solve problems medically and otherwise. My contribution, not a question, is that how do we bring this? How do we bring this? Like we do training all the time. Is it possible for our friend Abubakar to be invited in a way that we can present this thing? In fact, the thing is, one thing is the presentation, the other thing is doing the thing for people to see, to understand what it, because we train lots of postgraduate students and even some lecturers, and these are things that are needed because maths today is applications. Whether you are doing abstract algebra, you are doing pure mathematics, the end result should be applied to our own environment. So I want to know if it is possible that we can get his contacts whenever we think that we need to do some training, if we can actually contact him for also present at National Mathematical Center. Thank you.
Okay, thank you very much. So I'll just ask Dr. Abubakar to kindly respond before we now take some questions.
Okay, thank you very much, Prof, for your kind words. I appreciate. No problem, sir. Though I am currently in Malaysia, but whenever I return back to Nigeria around December, so I will. Anytime after December, there's no problem, sir.
It's okay. It's okay.
So that means you have an open what they call open invitation to the NMC in Abuja.
Yes, yes, sir. Yeah.
Right. So when you come in December, try to visit the director.
I will do.
Thank you.
Thank
Okay.
you. Thank you.
Now
So,
we
sir,
now
I
take
think
some questions.
I will
Hello,
have
hello,
I'm having a
hello,
contest.
hello,
Hello, sir.
Yes, who is
hello.
there, please? Who is there? Yes, sir.
Please, I'm still the director. I'm still here, please.
Okay, sir. Okay, sir. Okay, sir.
I want him to go back to the convergence. The equation I wrote to convergence. I didn't take note of this thing. The convergence equation that you talked about.
Convergence, the convergence analysis is omitted here, as I have mentioned that due to the time constraint. But I have a fully convergence result of this presentation, but it is omitted. But in order to present the convergence result, I have mentioned that we must made this assumption. So our convergence result it depends on this basic assumption. Our function must be uniformly monotone and the Lipschitz is continuous. But the theorem is omitted here.
Okay.
So we have some lemmas and the general convergent theorem.
So could you lead us to that paper? If you have maybe the reference, maybe you can type in the chat box so that students that are interested can also go to check that.
No problem.
Thank you. So can kindly help us do that before the end of the seminar. Okay, now we take some questions. Please, if you have questions, just look at the reaction button in your system and raise your hand up. Please, let's don't make it very rowdy. Just raise your hand up, by clicking on the key on your reaction box. Thank you. Dr. Ibrahim or Professor Ibrahim, please, can you go on with your question?
Good morning, everyone. Dr. Abubakar, thank you for the beautiful presentation. I have a few questions on slide 14 and 15.
14 and 15.
Slide 14.
Okay, slide 14.
Okay. My understanding is the motivation for your modification is to avoid the undefinedness of the denominator here, right?
Absolutely.
Yeah, if you go to 15, in your modification, equation 12, if the maximum is 0, this will reduce back to the original one.
Is the maximum
is 0?
Okay.
It will reduce back to the original one. And that same problem has not been achieved.
Okay, look at this remark, equation 14.
Okay.
So mentioned is the maximum
it will always be greater than 0 then, right? I get it.
We know norm of the norm can be 0. The norm can be 0, but here we say strictly greater than 0. Why? Because if norm of SK is 0, then we cannot even come to this point. The solution is achieved. So provided the solution is not achieved, norm of SK minus 1 is always greater than 0.
All right, I get the point. One other thing is the assumption you said F is uniformly monotone.
Yeah.
But in the conversion from minimization problem to nonlinear equation for the image part, F is monotone. So every monotone is uniformly monotone, but not every uniformly monotone is monotone. So how do the logic behind your method is uniformly monotone. So how does it solve a monotone equation?
Okay, before I answer these questions, what you have mentioned, I think reverse is the case. Every uniformly monotone is monotone.
Is it?
But not all monotone is uniformly monotone. But this, sorry, so in this Peng in their paper, this is an oversight. They have shown that their work is also uniformly or strongly monotone. It's not just monotone. So it's an oversight.
Yes, sorry, I stand to be corrected, but I think the monotone is a general map than the uniformly monotone.
Yeah, but look at the statements that you have mentioned. Every uniformly monotone is monotone.
And what I'm saying is that every monotone is uniformly monotone, but not all uniformly monotone are monotone maps.
No. Robust is the case.
All right.
Every uniformly monotone is monotone, but not all the monotones that is uniformly monotone. Because look at monotonicity here. Look at monotonicity. For the monotone here, we have can be 0. The inner product can be 0. But for the uniformly monotone or strongly monotone, we have there is a positive parameter C that will not let the right hand side to be equal to 0. So 0 is omitted in strongly monotone. That is why any strongly monotone is monotone, but not any monotone that is strongly or uniformly monotone. Yeah, monotone is bigger, but if you look at the statement that you have mentioned, it's like you have changed the order. Every uniformly monotone is monotone.
Thank you very much.
Am I right?
Thank you. So I see Andre is Professor Abdullahi Mohammed. Do you have a question or something?
Yes, sir.
Oh, okay. Please, can you go with your question? Thank you.
Yeah, thank you.
Thank you, Prof. You're welcome.
We can't hear you again.
Hello, can you hear me?
Yeah, okay, we can.
Yes. Can you
we
hear
can
me?
hear you now. We can hear you now.
All
Yeah.
right. I just have some few questions with regards to your presentation, particularly for the application part. You made mention that you apply your application, your proposed algorithm to solve some image application problem.
Yes, sir.
Particularly whenever you apply some blood or some noise or in the image, you apply your method to recover the noise. Is there any parameter that affect the noise, or you apply, you increase or you reduce to maybe to affect the noise of the image, so that you can apply your method to recover the noise?
Yes, there is though I suppose to include the Gaussian. It is a Gaussian noise that is generated randomly. So I think let me show you. So it has been omitted here. There is what we call the Gaussian noise, which is randomly. It is normally generated randomly. That is why we have this signal to noise ratio. But I get your question. You know, in the general, let me open one work so that you can see what I mean. Look at this equation. Sir, are you with me?
Yeah, we're with you. You can continue. Yes.
Okay, so this look at this phi. The normal equation that is for signal or image, we need it to be C bar is equal to A S curve. But this parameter phi represent the Gaussian noise distributed normally distributed within 0 to 10 power minus 4. So this is what caused in the in the uh, in the computational application, we are trying to remove this noise in order to have this omega to be equal to 0. Though it is not necessary to be 0, because if it is 0, then you have the original image. But we are trying to remove the noise, so it is changing at each iteration. So whenever you want to you are computing the application using MATLAB, you can see that this value is changing always because it is randomly generated, but it is approaches 0.
Okay, thank you.
All right.
Sorry, is it a
Dr.
typo?
Shaje, Dr.
Sorry, is it a typo
Shaje?
for that?
Sorry?
Could it be a typo because the noise should be added, right? Then you are trying to minimize.
Yeah.
Dr. Saje or Professor Saje?
Yes, sir. I'm sorry, sir. I still have one more question, if you don't mind, please.
Come again, please.
Yeah, I said I still have one more question, if you don't mind. My last question is that, Doctor, please, do you consider any other properties aside from this SNR and SSIM for the image recovery problem? Do you consider any other properties? Because we know there are other properties to be considered whenever you are recovering image, you are solving image recovery. Do you
Yes, there's also after this SNR, there is P.
We only consider this.
No, we also consider PSNR nowadays. Also, there is PSNR, which now it is even far better than SNR.
Okay.
So we are working on it now. The work is ongoing.
Hello, Dr. Abubakar.
Yes, sir.
Dr. Abubakar. Sorry, I have just a question. Can I go ahead?
Go ahead, sir.
Okay, thank you. Thank you for this wonderful presentation. I believe optimization is the way to go, and I'm so happy that you are even applying it. But one thing I just want to ask is about because I know most real life problems. Since we are talking about applications now, most real life problems most times they come in PD form. I'm just looking at it. Will it be possible to have this kind of problem in form of PD constrained optimization? Because all that you are presenting here is about a constrained optimization. And I'm looking at the equations that serve as the constraint there. They are more or less like although differential equation, but mostly ODE. Will it be possible to have a kind of most so that we're talking about application, and I know most real life problems are in PD form. Will it be possible? And because I also look at the trend, because I did some things in about optimization, most of the area of optimization that is trending now are PD constrained. Will it be possible to see how we can model or reformulate this kind of problem in PD constraint form?
Actually, I have never come across that idea, but okay. Maybe in the future we will look at its possibility.
So, sorry, I would like to have your contact. Why I'm saying this, because most of the people, like Professor Waziri, I knew him long ago, and even Leo Wanjua, probably your supervisor or probably the person you are working with, I also know him. Most of them have been working in this area of the organization. But of recent, I looked at it and I believe this is the trend where people are going PD, and I believe it will be very good if we can. And of course, it's very common among the Chinese people. Most Nigerians have not delved into this area of PD constraint optimization. I will be very happy. Probably maybe after this one, if you have your contact.
So we can collaborate. You know, Prof. Waziri is my mentor.
Yes,
he's my MSc supervisor. Also, he is my core PhD supervisor.
Yes, I know. I know him long ago. Even before he finished his PhD, they have been in this. So I will be very happy to have your contact so that we can talk better. I know this platform will not give us enough time to really discuss what I really have to discuss with you.
All right, thank you very much.
No problem, sir.
Yes.
No problem.
Yes, thank you very much. Dr. Shadje.
Yes. Hello. Good afternoon.
Good afternoon.
Doctor, wonderful presentations. Mine is comments and one observations. This is a wonderful presentation, Doctor. Oga at the top. Mine is about the issue of that uniformly monotone and monotone.
Okay.
In the first case, you say Dr. Ibrahim said that. Is he saying that every uniformly monotone operator is monotone, or every monotone is uniformly monotone?
He says that every monotone is uniformly monotone. I say no. The reverse is the case.
Okay. Yes, he said that.
Every monotone is uniformly monotone. That is what he says, if I could remember what he said.
Dr. Shadje. Dr. Shadje, we can't hear you again. Shadje.
Hello.
Hello.
Okay, yeah, you can continue. Yes.
Okay, that is my observation. That he said that every uniformly monotone is monotone operator. Since what we are talking about is the monotone operator as a muffin, right?
Yeah.
Okay.
Yeah, I think
so
we can.
it is
I think we can all go back to clarify this from the textbooks, so we don't overflog this. Okay, so I think I'll just take maybe I have just one question, and maybe we just go. Okay, so the question I just have, Dr. Abubakar, is I would just like you to the Newton's method is actually second order convergence.
Newton method is
second order convergent.
Yeah.
Yeah, so I don't know if you also try to investigate the convergence of this your new accelerated technique.
No, yeah, the certain techniques are linearly convergent.
Oh, linearly.
They are not converging faster than the Newton, but
okay, they are
yes, they are linearly convergent. Yeah.
Oh, okay. So, but what do you think? I'm just trying to ask, if they are linearly convergent, how do you think, in terms of iteration, what they call it, convergence, type of iterative convergence, which one do you think?
Okay, in terms of iterative convergence, definitely Newton converges faster than, because it is quadratically convergent, but it has some issues, as I have mentioned in the introduction. We have the computation of Jacobian matrix, and we know Jacobian matrix is a matrix of derivative. So if you have 100 by 100, machine will compute each and every derivative and store it.
Exactly.
Which is another problem, computational cost, storage location, and also it has the computational cost, because some derivative has no analytic solution. For example, you may come across maybe the Jacobian function that is maybe when you have the f over the t is equal to exponential minus t square. We don't have exact solution of this differential equation. So as such, Newton method cannot be applied directly. And another problem of Newton method is locally convergent. It is only converged within the neighborhood of the solution.
Thank you. Okay, so
and our method is globally convergent. Whenever you close your eyes and pick S naught on R, it will converge to the solution because it is globally convergent.
Thank you very much. And lastly, about my comments. So my last comment is going to be on the PD optimization, what they call it, constraint problem that professor was talking about. So yes, when you have PD constraint optimization problems, normally when you want to solve partial differential equations, the first approach is to discretize the partial differential equations into ordinary differential equations. So it will normally result to a system of ordinary differential equations. That's the idea. So, and there are very many partial discretization techniques you can use to do that. But since these problems are now coming with constraints, when you try to do a partial discretization of that partial differential equation, it now results to a kind of an optimization problem, which is what you are solving. So I think the starting point for you to collaborate in this research, right, together with people working in the area of PDEs, for example, I also do, and like that other professor that just gave the hint, is to first look for very good partial discretization technique for discretizing partial differential equations into some system of linear equations. So if you use finite difference, it will lead to some kind of linear difference, it will lead to some linear equations. So once these linear equations are going to be like the, what they call it, the objective function, and you have the constraints discretized as some kind of constraints, you know, then you have something like an optimization problem, which I think will be very good for you to look at and solve.
Okay, sir. That is a very nice idea.
I think in that approach, you know, I think in that approach we may be able to proceed with this kind of research.
So we can collaborate actually.
Exactly. So I think somebody wants to ask I think Dr. Zakari's question will be the last question before we go. I don't know if Professor Dekune is with us here. Okay. Dr. Zakari or Professor Zakari, your last take on this before we go.
Thank you, Mr. Presenter. It's not a question, it's just a comment. I would like to thank my mentor. Actually, the presenter is my mentor. Mr. Abubakar is my mentor. I learned a lot from your presentation, and we thank you for this wonderful presentation. Thank you, sir.
Okay. Okay, thank you so much, Dr. Zakari, for your nice, what they call it, your nice, felicitation to our presenter. Okay, so I want to use this opportunity to thank Dr. Abubakar for taking out time from his in fact, by now in China, it's supposed to be about 8 o'clock now. I'm sure it will be, we normally, in Malaysia.
Malaysia, yeah, almost 8 o'clock, yeah.
It's 7 o'clock?
8 o'clock, almost.
Almost 8 o'clock, yes, exactly, 8 o'clock. So I know this is the time where somebody really has with his family or time for him to do some personal things, but he has taken out of that time to be with us, to share his research with us, and to also teach us some of the things that he has been working on for some time. And also, during this presentation, the director of NMC has also, opened some arms of what they call it, request to him, and has also agreed that anytime we are having any workshop on numerical analysis at the National Mathematical Center, he will be mobilized to come and help us, understand some of all these topics, together with some also notable researchers in Nigeria working in the area of numerical analysis.
You are always welcome, sir.
I also use this opportunity to thank everybody for attending this seminar. Today, we had about 44 participants at this moment. I want to thank especially these 44 participants, and I want you to, keep up this spirit and try to network while you are here. Ask questions if you are a student. Please ask questions if you are a student, and also find opportunities to, improve yourself and meet people that you feel that can help you. On this note, I want to say thank you very much, and I wish that you enjoy the rest of the day. So our next seminar series will be in October, on the 3rd Wednesday of October. Thank you very much. Thank you, Dr. Abubakar. Bye-bye.
Thank you. You're welcome, sir.
Bye-bye.
So,